This is Michael Borenstein. Today I'm going to show you how to use comprehensive meta-analysis to compare the effect size in different subgroups of studies. Our website is www.metaanalysis.com. My email is michael@metaanalysis.com. I'm going to be working with a study that I set up a little bit earlier. I have it over here. I can highlight it, open it up. We have over here a total of 9 studies, Rawson, Gao, Lerner, and so on. In this case, we used the same data format for each study. We entered the effect size D with its confidence interval. For the first study, for example, we have a standardized difference in means of 0.45 with the lower and upper limit given over here, the sample size in each group given over here. The confidence interval is always 0.95, and the effect direction is auto, which simply means that the program is going to pick up whatever the effect direction was over here. If it was listed as positive, it's going to be positive, and if it was listed as negative, it's going to be negative. So we have 9 studies, and for each one we have a standardized difference in means, a standard error, and the variance. Once we entered the lower and upper limit, the program computed the standard error and the variance automatically. And we have one more thing over here. It turns out that the first 6 of these studies, these are all studies that looked at the impact of Naltrexone, which is a drug on helping patients remain abstinent from some kind of drug abuse. And where all 9 studies looked at that, it turns out that 6 of the studies had some kind of a mechanism in place to ensure that the patients remained in the study for a long period of time. We'll call those the high compliance studies, whereas the remaining 3 did not have that mechanism in place, and we'll call those the low compliance studies. And what we're going to want to do is to see if the effect size is stronger in the first 6 studies as compared to the last 3. What we do over here is we come out and we pick this column over here, which we're going to call retention, and we want to label some of them as high retention and the other ones as low retention. And the way we do that is we double click on this column. In this case, the value has already been entered. We gave it a name, which was retention. Then we have to assign a function to the column. And in this case, the function is that the column is a moderator. There are other options over here, but in this case, it's simply a moderator. And then we have to tell the program what kind of a moderator it is. And in this case, it's categorical because it's either high or low. And then we can say that we want this to be left aligned, which simply means that this label is going to be showing up on the left side of the column rather than, for example, in the center or the right. And then over here we had another column which we called year. We're not going to be using that in this analysis. Once I've done that, and I want to emphasize it doesn't matter what format we used for entering the data, it just matters that we have an effect size and variance for each study. And now we also have a classification for each study as either high or low. We can now go ahead and run the analysis. And so what we're looking at over here is we see the effect size and confidence interval for each study. There seems to be quite a bit of dispersion over here among the effect sizes, and a way to get a better handle on that is I can right-click where it says standardized difference in means. I can say sort it from low to high, and in fact you can see that there does appear to be a certain amount of dispersion. We have one study over here where the effect size is negative, suggesting that patients that were given naltrexone actually did worse than those that were given a placebo. We have a bunch of studies that fall in the range of no effect to a standardized mean difference of 0.5, and then one that falls a little bit above that. But we can also see that each of these studies is not terribly precise, so that in fact in most cases the confidence intervals overlap substantially. And it's not clear how much of this variation is real variation and how much of it is just due to random error. And I'm noticing over here that the Guerra study doesn't seem to have, we don't seem to be seeing an effect for that at all. If I come back and look at Guerra, it turns out, okay, well, the standardized difference in means over there was 1.57, which is the reason we're not seeing anything. I would need to change the scale over here. And so Guerra was all the way out here as an outlier. Let me again sort these so they go from low to high. Okay, so we have one extreme outlier. In any event, if we do a fixed effect analysis on this, we would get an overall estimate of the mean of 0.46 with a fairly narrow confidence interval. If we do a random effects estimate, the mean doesn't change that much. Let me look at both of them at the same time. In fact, the mean hardly changes at all, but the confidence interval is much wider. And the reason for that is going to be that there is a certain amount of dispersion among the studies, certainly if you include this one, and therefore we have a less precise estimate of the overall mean. We can come over here and click Next Table. You'll see that the p-value for a test of the null, in other words, for testing whether or not the true effect size is 0, in both cases the confidence intervals do not include the null effect of 0, and therefore in both cases the p-value is going to be statistically significant. But for the fixed effect model, the p-value is less than 0.001, whereas for the random effects model, the p-value is 0.021. And again, that reflects the fact that over here, the confidence interval is quite some distance from 0, whereas in this case, it's somewhat closer to 0, although it still doesn't touch 0, which is the reason that it is significant at the 0.05 level. Over here, again, you see those p-values of 0.000 and 0.021, which correspond to the two p-values that we saw over here. If we come back over here and look at the heterogeneity, what we're doing now is we're asking if the amount of dispersion that we see is something that we might be able to attribute just to the random error within each study, or if it exceeds that. And the Q statistic is 32 with 8 degrees of freedom, since there were 9 studies. Degrees of freedom is going to be 9 minus 1. The p-value is less than 0.001, which tells us that we can reject the null hypothesis that all of this dispersion is due to random error, and at least some of it is due to real differences in the study effects. Certainly this study over here is contributing to that, but obviously all of them are to some extent. The I-squared is 75, which means that if we look at all of this dispersion and ask what percentage of it is probably real as opposed to the amount that we would expect just based on random error and the fact that each of these studies is relatively imprecise, it turns out that about 75% of the variance that we're looking at is probably true variance. In other words, if we had a really good estimate of the mean in each study so that these confidence intervals were much more narrow, that the dispersion that we're seeing over here, 75% of that would still remain. The studies would not, in that case, line up all in a column or all in a row, but a good proportion of this variance would still remain. A good proportion of it really is due to differences between the studies. And the estimate of tau squared is 0.24. The estimate of tau is 0.49, let's say 0.50, which tells us that if we were going to go back and actually look at the standard deviation of these effects, that standard deviation is about 0.5, which tells us that if the overall mean effect is about 0.44, that we would expect that the true effects are dispersed about that with a standard deviation of about 0.5. In other words, we'd expect about 68% of the true effects to fall in a range of approximately 0 to 1, and another 25% or so to fall in a range of maybe minus 0.5 to 1.5. So there is quite a bit of dispersion over here. Given that that is the case, given that the true effects really do vary over a substantial range of effect sizes, the question that we logically would want to ask is, can we explain that? In other words, if naltrexone is such an excellent treatment in some studies, perhaps having an effect size as high as 1.0, and such a poor treatment in other studies, having an effect size as low as 0, are we able to explain that? Can we divide the studies into two groups and say, if you use naltrexone in this way, you're likely to have a really good effect, a really large effect, but if you use naltrexone in a different way, is the effect likely to be substantially smaller? And one logical candidate for this would be to divide the studies into those that had high retention and those that had low retention, and see if what we're thinking we might find is that in the studies with high retention, the effect size are consistently large, whereas in the studies with low retention, the effect size are consistently small. If that turned out to be the case, we would now understand what it is that makes this effective in some studies and not others, and would give us a way to pursue this, perhaps recommending that naltrexone should be used in one kind of study, in one kind of treatment and not the other, and that retention is a very important moderator over here. Well, since we've already defined retention as a variable and we've coded each of the studies for it, we can come back over here and say, let's see, analyses, nope, computational options, group by, and when I do that, I'm going to get a listing over here of all of the moderators that I have defined as being categorical moderators. You might remember that back on the main page, we also had a moderator that we defined as year, and that one was continuous, and therefore it does not show up over here. But retention was defined as categorical, and therefore it does show up over here. So I click retention, and then the program gives me an option of running the analysis within each level of retention and also comparing the two levels of retention. So I'm going to click both of those. I click OK. And let me, for a moment, I'm just going to click fixed effects just to make this a little bit simpler. What I have over here is an analysis at the top of the studies that had high retention and at the bottom of the studies that had low retention. And just to make this a little bit simpler to see, I also have now retained the ordering, so that in each case, within each of these groups, the studies are listed from the smallest effect to the largest effect. And what we can see is that in the studies with high retention, first of all, the means for these two sets are different. I can click over here. This button tells the program whether or not to display each of the individual studies. I'm going to turn that off for a second. And you can see that for the studies with high retention, the mean effect is 0.73 with a relatively narrow confidence intervals, whereas for the studies with low retention, the mean effect is about 0.13. So there really is a very dramatic difference between them, which would seem to support the idea that if you take studies with that enforced high retention, you're going to get a much larger effect. If you take studies that had low retention, you're going to get a much smaller effect. And if we were going to go ahead and compare these, the way that we would do the comparison is it would be this mean versus this mean divided by a standard error, which is based on this standard error and this one. Actually, we sum the variances and take the square root of that. But if we wanted to see what that looks like, we can come back over here where it says next table. We have the analysis on the top. Here's 0.73 for the high group, 0.13 for the low group. Here are the standard errors and the variances. And then over here, what we have is essentially the same as an analysis of variance table. The Q statistic for the 6 studies that had high retention, the Q value is 20, representing the amount of dispersion within the 6 high studies, degrees of freedom, and a p-value, which is 0.001, which tells us that within these 6 studies, there is a significant amount of dispersion. In other words, the dispersion that we're seeing within these 6 is more than we could attribute to chance. Similarly, if we look at the next 3 studies, we get a Q statistic of 1.4 with a p-value of 0.43. That is looking at the question of within these 3 studies, is there evidence of heterogeneity? And in this case, the answer is no, there's not evidence that the heterogeneity exists. But looking at these, the amount of the dispersion that we're seeing over here, we can't rule out the idea that there might be dispersion. We're simply saying that with only 3 studies, we don't get a statistically significant effect. We have not proven that there is dispersion. But at the same time, it would be a mistake to say that these studies are necessarily consistent. We simply don't have enough information. Then over here, we get this Q value of 22. What we're doing over here is essentially, this again is similar to what you would do in an analysis of variance. We're saying if we take the amount of dispersion within these 6, and we take the amount of dispersion within these 3, and we do sort of an omnibus test to ask whether or not there's evidence of dispersion within each of the groups, but pooled across the groups, the answer is yes. The p-value over here is 0.003, which tells us that there is overall evidence of dispersion. Again, computed within subgroups, but pooled over subgroups. So what we're left with is this finding, what we have so far, that within either of the groups there is more dispersion than we would expect by chance. And we're going to come back to that in just a second. Finally, the number that we really are looking for is this number over here. This is for the variance between groups. And what we're doing over here is we are comparing, basically we're comparing this effect size versus this one using this standard error and this one. And the p-value for the Q statistic for that is 10.5 with 1 degree of freedom because there are 2 subgroups minus 1, and the p-value is 0.001. And that tells us that if we look at this versus this, we do have evidence that these 2 effect sizes are not the same, that in fact studies that had high retention are going to have a larger effect size than studies that had low retention. However, and just one more thing over here, the final Q statistic is 32 with the p-value of 0.001. What that statistic is doing is it's simply comparing all of the effects, either you can say versus the overall mean. So what we're really asking is there evidence of dispersion over here across all of these if we ignore the fact that some of them belong to one subgroup and some of them belong to another? What we really are doing, again, if you think back to an analysis of variance, this is an analysis that looks at each individual effect versus this. The Q statistic between, which we looked at a minute ago, looks at this and this versus each other, and then the ones at the top looked at all of these within this group versus this, and all of these in this group versus this. So we're taking the overall variance and breaking it down into parts. If we take this 32, we can break it down into the variance between groups, which is 10, and the variance within groups, which is 22, right? 22 plus 10 gives us 32. And we could further subdivide it by taking the variance within groups, which is 22, and dividing it into the variance within the first set of studies, which is 20, and the one within the second set of studies, which is 1. That's basically what we would do in an analysis of variance, and that's basically what we are doing over here. So that would be the result that we got if we used a fixed effect analysis within each of the groups. Again, this estimate over here is using the fixed effect model to synthesize these studies, and this is using the fixed effect model to synthesize these studies. There's one problem over here, and it's a very substantial problem, which is that it is not appropriate to use the fixed effect model in this case. Again, the fixed effect model begins with the assumption that all of these studies have the same true effect size, and so that when we synthesize them, we assume that there's no variation among these studies, and that these three studies share the same true effect size, and that there's no variation among these true effects. And we've already seen that that is not true. We know that that's not true because if we come back over here and look at, well, we can look at this statistic, which tells us that when we compute the variance within each of the subgroups and then pool it, the p-value is 0.003. In other words, there's very strong empirical evidence over here that the effect sizes within each of within the subgroups do vary. And similarly, if we come back over here and look just at the first subgroup, there's very strong evidence that the effect sizes vary. So once we have evidence that these effect sizes are not coming from a common, they don't represent a common effect size, it is no longer appropriate to use the fixed effect model. Rather, we need to go to the random effects model. And when we go to the random effects model, although this point estimate and this point estimate don't change very much, but the confidence intervals in each case become a lot wider. And if we look at them over here, you can see that we're looking at 61 versus 0.61 versus 0.15. Previously, we were looking, I think, at 0.73 versus 0.13. So these estimates are not a lot different than they were before, but the confidence intervals are much wider, and now they overlap quite a bit. So the question would be, if we now go back and use these estimates with these confidence intervals, do we still have evidence that this effect is different than this one? And if we come back over here and look at it, in this case we have to come down over here where we're looking at a mixed effect analysis, and the Q statistic for that is 1.59, 1 degree of freedom. The p-value is 0.207. And that p-value, again, is the comparison of this versus this using this standard error and this standard error. So when we do use these wider confidence intervals, we no longer have evidence that, that the mean effect for these studies is different than the mean effect for these studies. And so in this case, that would be the conclusion that we would reach. There is no evidence that the studies are different. There is one other thing I need to point out to you over here, which is pretty important. There are different computational options that you can set over here. If we click on computational options and go down to mixed and random effects options, over here we have studies within a subgroup. That would be these studies over here or these studies over here. Do we want to assume a common among study variance component across subgroups, or do we not want to assume that? What this means is this. What we're always going to do, regardless of which option is selected over here, is we're going to compute an estimate of tau square. We're going to compute an estimate of the between studies variance within this group of 6 studies. And then separately, we're going to compute an estimate of tau square within this group of studies. That's always going to be the case. But once we've done that, we have 2 options. One option, the one at the top, is that after computing tau square over here and computing tau square over here, we then pool those 2 estimates to get a common estimate of tau square. And once we've done that, we then apply that estimate to all 9 studies. The alternative is that we can use these 6 studies to get an estimate of tau square, which we then apply to these 6 studies, and then we look at these 3 studies to get a second estimate of tau square, which we apply to these 3 studies. You can actually see how that works if we go to the table of calculations. For the moment, I've checked the first box, which says that we do want to pool the 2 estimates. So if we come over here and look at calculations, you can see that the estimate of tau square, in fact, let's go back over here for a minute to the next table. We see over here that the estimate of tau square in the first set of studies was 0.29, and in the second set of studies was was 0. But if we come back over here and we pull them, the combined estimate is 0.18. And once we have that combined estimate, that estimate is being applied to the first 6 studies, and also it's being applied to the next 3 studies. By contrast, if I go to computational options, pick this, and say I don't want to pool them, then what happens is the estimate of tau square for the first studies is 0.29, and that's applied up here, and the estimate of tau square for the second studies is 0, and that's the estimate that's being applied down here. You might also notice that none of those is the same as this number over here, 0.24. This would be the estimate of tau squared if we ignored the subgrouping. But as I said a minute ago, that is not what we are doing over here. In this case, we're computing the estimates within the subgroups and then either pooling them or not pooling them. And by the way, if we take this second option, which we've done now, and we don't pool them, then when we come back and look at this p-value, which is now 0.10, rather than it had been a minute ago, which was 0.2. If we look at this, come back to the basic stats, you will see that these estimates over here have also shifted a little bit. Now, okay, now we're looking at 0.60 versus 0.13, so those means have changed a little bit because they're being assigned different weights. At the same time, this confidence interval is now much more narrow than it had been a minute ago, whereas this one is wider than it had been a minute ago. The point is, the point is simply that depending on which of these options you select, you're going to get different estimates for the means, and you're going to get different estimates for the confidence interval. So the question is, which option should you select? And the answer is, in general, it's better to select the option that we're going to pool them. And the reason is that in most cases, and I want to make it clear that this is just sort of a general rule and you have to evaluate on a case-by-case basis, but in many cases, let's say, there's no reason to believe that the dispersion in one group is going to be different than the dispersion in the other group. In most cases, the kinds of dispersion that we're going to be seeing in effect sizes is going to be relatively comparable within all of the different subgroups of studies. So the fact that we happen to see more dispersion here and less dispersion here, that in itself is probably more a function of chance than of real dispersions among the studies. So if we really had a reason to think that there would be a lot of dispersion among these and less dispersion among these, then it would make sense not to pool them. On the other hand, if we don't have that, but conceptually it makes sense to think that we're going to be seeing around the same amount of dispersion in both, the advantage of pooling is that to whatever extent these estimates are subject to random error, by computing an estimate of tau square based on 9 studies, we're getting a more accurate estimate of that tau square than we would if we had one based on only 6 studies and one based on only 3 studies. In fact, getting an estimate of tau square based on 3 studies is really a very iffy proposition. That estimate is probably going to be way off. So even if it is the case that the amount of dispersion really is different here than here, the chances are that your overall accuracy is going to be better if you pool these 2 estimates so that you're working with 9 studies rather than 6 studies and 3. And just to say that again to make it a little bit more clear, while we might be introducing a little bit of error by saying that we're going to pool these and ignore the fact that there might actually be more variance here than here, we might be introducing a little bit of error that way. But it's probably less error than we would get if we worked with only 6 studies and only 3, because that is a much more potent source of error. And therefore, in most cases, or at least in many cases, I think the default position would be to pool the values rather than use separate estimates of those values. So that's what I've chosen to do over here. Now, a question that, notice that when you're working with the fixed effect model, of course, this doesn't matter because tau square is simply set to 0. But when we're working with the random effects model, it does make a difference. Again, over here we can see the weights that are assigned to each of these studies. Over here, these weights sum to 1, and then these weights sum to 1. We can do that using the fixed effect model and the random effects model. You're going to be seeing the same things over here that we saw when we did not use subgroups. Looking down here, for example, the weights are, the large study is given the lion's share of the weight. These two studies are given much smaller weights, whereas over here the weights are much more balanced. And that's what we're going to do. We're going to go with the random effects model. And then coming back over here, this is probably the p-value that is it's most appropriate. We can come back over here to the next table. We can get rid of the weights. We can say I'd like to do a high resolution plot. We can change the title, make this Naltrexone. And then what we have over here, these are the individual studies for the high retention group with the overall effect. These are the ones for the low retention group with the overall effect. We can modify this a little bit. And we can change these symbols over here. Let's say if you're studying summary symbols, we'll go to the subgroups and we'll make those red. And that's the basic idea. Again, we can send this off to, we can change the color, send it off to PowerPoint or Word. We would need to change the color separately over here because when we change colors, it's for either the printing scheme or for the PowerPoint scheme. So if I come back over here and I want to change the subgroups and make them red again, I can do that. I can go to the overall summary and make that yellow, and so on. I'm not sure these colors are the best ones to choose, but the basic idea is that you do have the option of modifying all of this. Okay, I should point out that in this particular example, we were using studies where each study gave us one effect size. All of the subgroups are completely independent of each other. In another one of these videos, I'm going to show you how to deal with the case where a single study gives you more than one estimate of the effect size and where those estimates are not independent of each other. In that case, we have to deal with the non-independence of studies, and we will handle that separately. Again, the website is www.metaanalysis.com. My email is michael@metaanalysis.com. Thanks very much for your attention.